we now need to solve problems involving capacitors when they are connected in parallel. But we must understand what parallel connection of capacitors is all about. Capacitors are said to be connected in parallel when they are connected side by side. Look at my hand, side by side, okay? As if you're building a building block, so to say. That's interesting, right? When capacitors are connected side by side, they are said to be connected in parallel. But if they are connected end to end in a chain form, they are said to be connected in series. In case you have not watched my video on the topic series arrangement of capacitors, I urge you to go and watch it. Okay? Thank you. So let's do that. We have parallel arrangements of capacitors. Look at this. Parallel arrangement of capacitors. It can take any shape, but make sure the bars of the capacitors being connected are equal. Okay? The two plates must be equal. Alright? Alright, so that is it. So let's put it in a very proper way. Yes, that will show seriousness of what we are doing. Okay, so we have this. So with this, we can now calculate. So if we have this, we can calculate what happens at this point. If we have this is C1, this is C2, and this is C3, we can as well have a situation where the parallel arrangements, the number of capacitors being connected, just two. So if we have two capacitors in parallel, we have something like this. There's nothing, only that the number will reduce. There's no difference from what we already have. So we have this. Okay? I'm just trying to represent two capacitors in parallel. This diagram represents two capacitors connected in parallel. This one, the first one, represents three capacitors connected in parallel. Just what opposite of what we learned in our previous video, right? Okay, so we have C1 and then C2. What do we do? Very simple. In fact, this is the simplest way to calculate the total capacitance when two or three capacitors are connected in parallel. Simply say that this can be calculated. The total capacitance CT is equal to C1 plus C2 plus C3. Very simple. That's what it means. There may be plus dot 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 dot. If there is any other capacitor to be connected, very simple. So if the same thing applies here, CT is equal to C1 plus C2. We are going to stop at C2 because we have only two capacitors connected in parallel here. So solving this is very simple. If we have, in figure 1, we have maybe 3 microfarad. And we have here 4 microfarad and probably 6 microfarad here. And we are asked to find the total capacitance in figure 1. In this figure, it's simple. What we need to do is CT is equal to, for C1 we have 3, alright? For C2 we have 4. And then for C3 we have 6 microfarad. Then we total. 3 plus 4 is 7, 7 plus 6 is 13, and that gives us microfarad. Microfarad. Alright? We can as well extend this to be 13 times 10 raised to the power minus 6 farad, which is the original unit of capacitance. Look at it. This is interesting. And my students will learn this with confidence. They won't find it difficult. Do the same thing here. If we do the same thing here, it means we have also CT is given as 13 times 10 raised to the power minus 6 farad. Why do we have this? Simply because microfarad value is 10 raised to the power minus 6. So this has been replaced with 10 raised to the power minus 6 farad. That's what you're seeing here. We can still do the same thing here. To find the total capacitance, please, if this is 4 microfarad, and then this is 5 microfarad. This is 5 microfarad. What do? We come down here. CT is equals to 4 plus 5, all equals to 9 microfarad. All right? Very simple. But we can extend this to be 9 times 10 minus 6 farad. Very simple. That is it. It's been solved. It has been solved. So I want to remind us that this method holds only when the capacitors are connected in parallel. Don't mistake this for when the capacitors are connected in series. No, don't do that. Otherwise, you will arrive at a wrong answer. Let me also remind us that the capacitance of the capacitor depends on 4 things. 4 things. The capacitance depends on 4 things. Okay? These things are, number 1, the size. The size of the capacitor. That's number 1. Number 2 is the nature. The nature of the dielectric substance separating the 2 plates. That's number 2. Number 3 is the distance. The distance between the 2 plates. D. Okay? Dielectric substance here, E. And then size somewhere here. That's the 3rd one. The distance separating the 2 plates. And the 4th one is the shape. The shape of the capacitor goes a long way determining the capacitance of the capacitor. So if these 4 things are taken into consideration, we'll be able to say that the capacitance of a capacitor is this or that. So we must note this. Very, very important. When the distance between the 2 plates increases, capacitance of the capacitor reduces or decreases. I repeat, when the distance between the 2 plates increases, the capacitance of the capacitor decreases. Take note. Increasing the cross-sectional area of the capacitor plates, of the 2 plates, also increases the capacitance of the capacitor. When the cross-sectional area of a capacitor increases, correspondingly, the capacitance will also increase. If it reduces, correspondingly, the capacitance will also reduce. This is interesting. If you have watched up to this moment, come on, what is happening? Subscribe, thumbs up, push on the bell button for constant notification. Share with your friends, networks, and students. All right? I want to end it here. If there is any point you don't understand, put it in the comment section. I will address it. In fact, if there is anything in any of my video you don't understand, come on, give me a call by putting it in the comment section. I love you guys. Thank you so much for watching and for patronizing me. Belong to this community, great teachers community, great learners community, and we will continue to explore teaching field. Thank you. See you in my next class.